Welcome everybody to the second CSS seminar series. I'm happy to introduce you to Professor Morgan Frank here. He is an assistant professor in the Department of Informatics and Network Systems at our neighbor University of Pittsburgh. He does really fascinating work in the area of computational social science, in particular future of work and how technology is shaping and changing the prospects of different occupations. So we had a brief conversation about how creative work, for example, graphic design, might change in the future due to these different AI systems that are basically doing a lot of creative creating a lot of creative artifacts. So I believe today's talk will be somewhat related to that issue as well. Without further ado, I turn it to Professor Frank.
All right. Thank you so much, Patrick, for the warm introduction. I'm excited to tell you about my research on skill complexity and the future of work. Today, I hope to motivate you a little bit about why thinking about technology in the context of what work of the future will look like is a reasonable endeavor and also a challenging endeavor. I'm going to touch on some key results from a few different papers that I think form a single cohesive framework for thinking about this problem and why using the word complexity in the context of skills in the future of work is actually the right way to go about this. In the end, I'll point you to these papers if you want to learn more, and of course, I'll be happy to answer any of your questions about this. So let's get started. So there's a lot of excitement and interest about new AI applications. The ones that I'm highlighting here, for example, include things like natural language processing, which is on everybody's phone in your pocket right now. Self-driving cars seems like a thing that may or may not happen in the next 50 years, and maybe 50 more years, or maybe 50 more years after that, we'll see. But if it does happen, it has drastic implications for what the transportation infrastructure of the US could look like. You could imagine prices dropping significantly as the cost to move goods drops as well. Maybe some more up-to-date and exciting examples include things like computer vision applications in medicine to do things like radiological work. And the example we were talking about over lunch was stable diffusion applications and things like DALL-E that stand to potentially replace the need for graphic designers and instead replace this need for artistic ability in terms of visual arts with prompt engineering. In any case, you can look at the growth of AI startups or even other things like AI patent production in the US or in China or in Europe over time, and it seems that AI is booming. It represents a frontier for innovation and entrepreneurialism. However, not everybody is so enthusiastic about what things like tech and AI mean for the future of work. In fact, a recent Pew survey from 2018, I think, so before the pandemic in any case, found that a majority of Americans are worried about the future of work and don't think that there will be new jobs in the future. There is some aggregate evidence to back up this concern. Here, for example, the blue curve, we have gross domestic product. So think about this as the productivity of the US economy steadily growing over the years. The red line is the real median income. And what you can see is that for years, for decades even, these two curves grew together. But in the last couple decades, there's been what's called the great decoupling. And there's been a ton of work from labor economists to understand what factors contribute to this decoupling. And it's been thought that the growth of tech industry and the wealth inequality that has come along with that has been one of those factors. So let me point to a more specific example about why we should be talking about technology in the context of the future of work, just thinking about COVID-19 and the recent push to digital work and work from home. It's expected, for example, that 25% of North American professionals may work remotely by the end of this year, 2022. Compare that to 9% from before the pandemic. So that's a huge growth. This is a new challenge for both workers and for workforce development. So for example, what education gives workers the right digital skills in addition to whatever else they were doing on the job before to be able to work in this new context? How can existing workers who are beyond educational institutions adapt on the fly to these new demands and adapt to using email and Zoom and Slack even if they weren't doing that before? And how can employers identify workers who can meet these new labor demands? This transition is really about digital literacy, proficiency with digital tools, and adaptability to the future of work. And what I am going to argue is that all these things have to do with skills. What skills do you have? What skills can you learn based on the foundational skill set you already have? And what does this mean for your adaptability to the future of work? One final observation that's going to pop up later is that this work from home and this phenomenon of urban flight, for example, from the most expensive cities in the US, think the Bay Area and Manhattan, this clearly relates information workers who are able to do digital remote work and urbanization. And so this is to say that the future of work and the role of technology in shaping it has a spatial component as well. We're going to talk more about this. So for now, let's focus on just these three questions. Which workers are exposed to technology? Where are these exposed workers located? And are exposed labor markets resilient to this type of change? So in thinking about how economically robust cities are, there's a real wealth of information out there. So here I'm thinking about a very well-cited book called The Triumph of the City from economist Ed Glaeser at Harvard University. In this book, he talks about how cities are this great system. It's basically a rising tide that floats all boats. He shows, using mostly data from the 70s and 80s, that regardless of your education or your gender or your ethnicity, compared to similarly situated peers in smaller cities, you are better off in larger cities. So there's this benefit to being in a large city. But even Ed notes that this need not be the case because not every city will succeed at adapting in the age of information, or maybe adapting because of a global pandemic. You could imagine tons of other shocks that might reshape cities as well. There's some evidence to back up this concern that shows that the urbanization that we are used to thinking of in the 70s and 80s has deteriorated into a completely new trend. So these three plots come from David Otter's paper called Work of the Past, Work of the Future. I got to talk to him about this while he was preparing his AEA Eli lecture on this, and he told me this was probably the biggest result of his career. And what we're looking at here is each color represents a different decade. He's dividing workers into different levels of skill: low skill, middle skill, and high skill. And the x-axis is the population density of the city. This is going to be correlated with city size, for example. The y-axis is the change in employment share as a function of the density of the city you're in. What you can see is that low-skilled employment is shrinking in large cities throughout the entire time period. Middle-skilled workers were experiencing employment growth in earlier decades, so there was good growing support for middle-class families. But this effect has actually deteriorated in most recent decades. It's actually started to diminish. And now, in large cities, only the most highly skilled workers are able to effectively urbanize for one reason or another. Who are these high skilled workers? They're workers who can work with technology. They have college education or sometimes even higher education like master's degrees and so on. But why is this shift? And this, again, challenges our preconceived notions about what makes urban economies resilient, and are they still resilient today? So what makes a city resilient? Again, like I've mentioned, there's lots of work on this we can pull on. Here, I'm making reference to a very well-celebrated urban demographer, Jane Jacobs. She's one of the first very prominent female voices in this research community, and she did a lot of really important work here. For example, she has a children's book written about her. So I don't really care what your H index is. You haven't made it so you have a children's book created about you. That's impact, people. Anyways, some of her big ideas are built on the idea that cities need to be diverse. For example, she says that it's fatal to specialize, and all kinds of things show us that the more diverse we are in what we can do, the better. So diversity is key to making cities resilient, both in a social context, but also in an economic context. Okay, so with this in mind, let's start thinking about which cities are most exposed to disruption from technology. How are we going to do this? Well, there are a lot of efforts to estimate which workers and which job titles are most at risk of automation. Here, I'm pointing to a whole bunch of them. I got, 8 of them here. We're going to come back to this, so don't worry if you don't get to read the whole table now, but it's just to show you that there's a lot of work going on here. So my first effort to study this question was to combine these per occupation level estimates for automation risk with the employment distribution in different cities to arrive at this on average weighted estimate that I'm calling expected job impact from automation. So here's a map coloring cities using one of those sets of occupation level scores from the Fry-Osborne study out of Oxford University. This was one of the earlier efforts in this space and received a lot of attention. The bluer cities have lower expected impact, while the red cities have greater expected impact, according to this really simple calculation. So you can see, first of all, there's a lot of heterogeneity across different cities. And if you kind of squint at it, maybe you would see that the large coastal cities are more blue in general. We can quantify this a little more concretely with this scatter plot on the right, where we see that in general, small cities should expect greater impact from automation in the foreseeable future, at least to our first order approximation. This was the result. We found this with the Fry-Osborne estimates, but also swapping in a few of the other ones from that list from before, you again see this negative relationship between city size and expected impact from automation. So the question is, what's going on? What factors might help us understand this differential impact from automation across cities of different sizes? So to talk about resilience and diversity in a labor economic sense, there's already some tools for doing this. For example, talking about shallow or deep labor markets is a tool you might use to talk about diversity. The idea here is that a shallow labor market will have fewer unique job titles compared to a larger city or a deeper labor market, which has more unique job titles. And you would in general expect larger cities to have deeper labor markets. But this simple approach misses how employment is actually distributed amongst these different categories. So what we find is that when we look at small cities, there are fewer bins, but actually the distribution of employment is a little more uniform compared to when you look at the distribution in larger cities, which have more bins, but also have this greater skew in the distribution. So I'm not sure what all of your backgrounds are here, but I bet that there's a good bit of computer science and information science here, right? So if you're looking at this distribution and thinking, how do I measure diversity? Entropy probably comes to mind, and that's what happened for me as well. So let's think about using entropic measures to talk about diversity and specialization in these distributions. We're going to look at this three different ways. First, we're just applying normalized Shannon entropy to those employment distributions over occupations on the left-hand side here. So each circle is a different US city. In the middle, we're going to take skill profiles for each US occupation provided by the US Bureau of Labor Statistics, combine those with the employment distributions in each city to create a skill distribution, and then apply normalized Shannon entropy again for the middle. This rightmost plot is using a multi-level entropic measure called tail entropy. In this case, it's basically measuring the relative abundance of relatively specialized workers in each city. Across each of these cases, we observe that larger cities are more specialized. They have lower diversity according to these information theoretic measures. So now I see that most of you look like maybe PhD postdocs. I want you to imagine being in the middle of your PhD, which is where I was when I said, oh shoot, this really strongly disagrees with stuff like what Jane Jacobs was saying about diversity being the strength that helps these cities adapt. She says it's fatal to specialize. So my analysis came up with some disagreements, which to me raised a few possible issues that I've done a lot of work to try to address, and I'm still doing more work now. So first of all, what are some possible issues with what I did? One thing is that our measures for technology exposure might be poor. Maybe those are just noisy and it wasn't a good use case. Another idea is maybe just talking about market depth or shallowness, or even looking at employment distributions is overly simplistic. And we're missing out on information that's really valuable for understanding resilience. Maybe we need a different framework for thinking about this. So now let's think about these questions a little more concretely. Can we measure technology exposure and its impact on labor? And what are some possible outcomes or symptoms of technology exposure that we could look for? Okay, so some symptoms of technology exposure. Of course, there's the worst case, which is that there's unemployment as the result of a technological change. So maybe DALL-E removes the need for graphic designers at all, and there's mass unemployment. These graphic designers have nothing to do. This would be the worst case scenario. Probably this is not the most common outcome. I think that if you survey labor economists doing work in this area, they think that most of what's going on is that technology actually changes the demand for specific skills within each job. And that these changes to skill demand, maybe they're small and workers can adapt, and they just learn a new talent that allows them to complement technology, and they're able to just carry on and it's no problem. However, these skill changes can be larger, and maybe workers aren't able to adapt to find some new skills that complement technology, and they end up being replaced by newer workers who are able to complement technology, maybe younger workers in this case, who can work with digital tools that they are familiar with through college. In this case, it's really not clear what would happen to aggregate employment or aggregate unemployment for these occupations. If these displaced workers find new employment elsewhere and are replaced by new workers, maybe employment goes up for this occupation that was exposed for technology. If these workers fail to find new employment, maybe they become unemployed. But if you're just looking at aggregate unemployment counts, which is what's typical using data from the Bureau of Labor Statistics, maybe you would actually fail to be able to connect these benefit seekers from the occupations from which they were displaced. So in any case, we need some more information, and we need to pay more attention to all the possible outcomes that can occur. So with this in mind, let's return to this table that we breezed over a little bit before. I would say that this is a pretty good sampling of the most high-profile efforts to assess automation risk across different job titles. And what you can see, first of all, is that these examples span the last decade. This is not a new problem. People have been trying this for a while. And roughly speaking, I'd say there's been 3 waves of efforts to assess automation risk for occupations. The first wave was very theory-based. We have skill-biased technological change that tells us that in general, high-skilled, cognitive, non-routine workers are augmented by technology and made more productive, while low-skilled physical workers tend to be replaced by physical technology like robotics or self-driving cars. That's the prevailing wisdom. What do you mean by low skill or high skill, you might ask? Patrick, are you a high-skilled worker, would you say? What do I even mean? Yeah. So I asked David Otter, what do you mean by this? And he said, well, these industries and that industry. I said, well, how'd you pick those industries? He goes, they have bachelor's degrees. This is often the metric that they use empirically for this abstract thing. So that's wave 1. Wave 2 gets a little more specific about skill requirements for different occupations. Most of these studies are using occupational skill profiles from the ONET database, which is this annual survey done by the US Bureau of Labor Statistics. They detail 700 different job titles in the US and tell us how important, in the case of the studies I'm going to share with you, how important a vector of about 300 different skills, knowledge, and ability are to each of these occupations. And here in these studies, they're trying to assess how automatable those skills are, how important those skills are to occupations, and then using that to assess each occupation's risk. The more recent effort, wave 3, these are examples where they try to be more specific about what technology can actually do. So for example, go out and surveying machine learning experts and saying, what do you think machine learning can do? Can we survey them, get some ideas, use that to assess the tasks that are required by different occupations in this ONET database, and then score each occupation. Or maybe even looking at NLP patents, for example, and using natural language processing to compare AI patents and what the technology can do in the patent description to these job descriptions and saying how much overlap is there as well. So trying to be more concrete and matching skills to technological capabilities. The problem here is that if you go look at each of these studies, the waves seem to kind of build on each other. And how do they validate their scores? They all do the same thing, actually, which is to show that employment for exposed occupations has decreased and wages have decreased. It's all the same. There's no effort to look at unemployment because looking at just aggregate unemployment by state lacks the variability by job title. It's not a good data for testing that out. And there's no effort to look at job separations also because it's kind of difficult to disaggregate these state level data to get down to the occupation level. Okay, so let's look at these scores. Again, remember, I ended up in a confusing place in the middle of my PhD. Let's try to figure out how this happened. So first of all, these scores have been growing across these different waves. Here I'm using some shorthand, but it's the same. It's measurements from those studies I mentioned before. If they are building on each other, maybe they're converging on a single answer. Each iteration is a slight improvement on the last. So here we're just looking at how correlated, it's just a correlation matrix, And what you can see is that for the most part, the correlations are all over the place, sometimes positively associated, sometimes negative. The strongest relationship is between a measurement for exposure to AI and exposure to robotics, but those measurements actually come from the same study, the same paper. And everything else is actually kind of small. So doesn't seem like there's some convergence. On the right-hand side, again, we have our different measurements from those studies in that table on the y-axis. The x-axis, each vertical stripe is one of these 700 job titles, and I'm aggregating them based on major occupation types so you can get a sense. So again, if you pick these vertical stripes and look at them, it looks noisy, right? So not very good agreement across the same occupation even using these different measures. So this sort of begs the question, can we measure technological exposure? What are the outcomes from technological exposure? And does exposure to technology actually lead to unemployment? So this is some ongoing work, and I'm excited to test it out on you guys. So I'd be curious to know what you think. But I have some new data that I think makes it possible to assess unemployment risk at the per occupation level. So again, a lot of these other studies have access to just how many people received unemployment insurance benefits in your city or in your state, but not any information about what were the gender of those people, what was their most recent occupation. I've overcome this hurdle. Me and my collaborators have accumulated data from every state's unemployment insurance benefits office, monthly data detailing the most recent occupation of everyone who received insurance benefits each month in that state. So if you can imagine, this is telling me, given that you're unemployed, what's the most recent occupation that you had? And then combining this with some other employment statistics you get from the Bureau of Labor Statistics, so standard stuff, we can do a little Bayes theorem here to get at what I think is more interesting, which is what's the probability that you will need unemployment benefits given your occupation, and also the state and the month. So I'm thinking about this as unemployment risk by occupation. So how do our scores do at predicting unemployment risk? So here again, each bar is telling us the Pearson correlation between log unemployment risk by occupation, month, and state. It's just a straight correlation. Again, you can see that there's some variability in the sign, even within the same wave. But if you look at this inset, there is in general some improvement from wave 1 to wave 2 to wave 3. But how big is this improvement? It's tiny. If you look at all these different measures in, say, the wave 3 category of measures, the median predictive performance achieves an R-squared of 0.2. It explains 2% of the variation in unemployment risk. So that's not very good. So this suggests a few possibilities. First of all, maybe technology is not a factor in unemployment, and this was a waste of time, and we don't need to worry about technological unemployment. That's possible. Another possibility is that we saw that these different scores don't really converge. So maybe we're just not good at measuring technological exposure. And so again, it's sort of a futile effort. But I'm a computer scientist, and so I also tried the kitchen sink model. And what you see here using a lasso regression, again, not really being careful with controls, is that although individually they're all really poor at predicting unemployment risk, taken together, they account for 20% of the variation in unemployment risk across occupations. If you add some very reasonable controls, like what are the fraction of workers with a bachelor degree in each occupation? Here we're controlling for skill requirements across occupations, year fixed effects, month fixed effects. So you could think about year fixed effects controlling for like long-term dynamics, like recovering from the Great Recession. Month fixed effects would control for seasonality. State fixed effects would control for spatial heterogeneity. There's Silicon Valley in California, but maybe not in like rural Nebraska. Even with these controls, you achieve an additional 12% variance explained with this kitchen sink approach. And it's interesting, if you look at the coefficients associated with these individual scores, this is far from causal, but many of them are significant. So what this tells us is it's not one or two of these studies that are doing the work, it's all of them combined. So for me, what this says is that individually they're doing poor, but there are several of them that are picking up on different parts of the technology and the future of work story. So we need to do some more work to understand what is effective, where and when, if we want to understand where technology exposure is occurring. What about additive sample testing? The highlight of the last slide was about predictive performance. So here we're just doing the similar test where we have a baseline model with controls for years and months and so on, and doing cross-validation with and without our automation measure, and you see a similar improvement in performance. What about predicting aggregate unemployment at the state level? Again, similar performance improvement. Also looking at job separation rates at the state level. So this is weighting the employment distribution in each state by its exposure score according to these different measures. And then finally, perhaps the most interesting is looking at the within occupation change to in-demand skills using that ONET database as a function of how exposed to technology that occupation is. And you can see that the factor improvements for this within occupation skill change is the greatest here. And maybe this is some evidence to back up this general thinking that's coming from the future of work community, that it's within occupation, labor reorganization, that's the main story, and the thing that we need to focus on moving forward. So what do I mean by this? Again, it's this idea that technology performs specific tasks, right? That computer vision algorithm that's really great at detecting cats, it's really great at detecting cats. It's not really great at writing music or driving a car. It's specific in what it can do. And the skills that will change as a result are also very specific. We need to get down to skills. Okay, so for now, what we've learned is that quantifying technology exposure is hard. I don't necessarily know how to solve this problem. So is there a more general framework we can use to talk about economic resilience in labor markets? Okay, so let me give you an idea about how I'm thinking about economic resilience from the perspective of technological change. So I mentioned this idea called skill-biased technological change, which is where we're going to start as well. It's in general the idea that high-skilled cognitive workers are made more productive by technology and stand to benefit from technological change, but low-skilled physical workers tend to be substituted by things like robotics. So let's look at this example of a robot in a warehouse. So this is from Boston Dynamics. They make robots. And I show you this because it's really cool. But also think about what this robot would mean for employment for humans in a warehouse setting, right? So I've provided some YouTube comments for this video here, not usually a great source for economic forecasts, but in any case, you can see that they're pretty negative here. They don't think that this is a good situation for warehouse workers. And again, this is well within the skill-biased technological change paradigm, right? Warehouse work is physical, and physical workers tend to be replaced by things like robotics. But I think that if we're forced to just talk about occupations in just this very abstract way, we're missing out on a lot of really useful information. So here's another illustrative cartoon example, but I think it will highlight something we're missing out here. Okay, so let's see. Here we see an artisanal good produced by a high-skilled worker. Here we see two unskilled workers. But using some technology, we can produce this artisanal good with these unskilled workers. So in truth, these two folks, I think they're computer science grad students at UC Berkeley. I'm sure they're going to be just fine. So here in this scenario, again, it's kind of cartoon, but I imagine this is how we produce dance in the future. I don't think that's likely, but just imagine. I think that this scenario would depress wages and depress employment opportunities for the skilled ballerina because the ballerina is expensive. But it would create more employment opportunities and maybe greater wages for the low-skilled workers in this case, who can work with technology cheaply. So this stands as in contrast to the warehouse example, where the low-skilled workers were replaced by the robot. So let me give you some more concrete examples of this. If we're forced to talk about occupations using just the skill-biased technological change framework, you're forced to put very different job titles into the same categories. For example, medical surgeons and civil engineers, these are highly educated, cognitive, non-routine, high-paid occupations with entirely non-transferable skill sets. There is nobody out there who is switching between these two job titles in their career, probably, right? And further, the types of technology that these workers are likely to interact with are going to be really different. So if you want to understand how technology will shape the future of work for these two job titles, you need some more information in what's different about the skills and what is it that these technologies can do. There's another well-documented example actually from the literature. Let's do a little survey here. What do you think happened to national employment for bank tellers with the invention of automated teller machines? Okay, so there's three options: decreased, stayed the same, increased. Who goes for stayed the same? Raise your hand. Okay, so maybe 2% for stay the same. What about decrease? Raise your hand. Okay, a few more. So that was more like maybe 50, 60%. And how many for increased? Okay, so more like 10, 20% for increased. The answer is it increased nationally with the advent of ATMs. You can read more about this by looking at research from James Besson, who's an economist at BU. He points to two reasons for why bank teller employment grew. The first is that the demand for bank goods and services scaled superlinearly as it became cheaper to open bank branches. So basically more bank branches opened nationwide, but they were smaller bank branches because ATMs did most of the services that and allowed banks to open with less space. So there were fewer employees per bank, but more bank tellers at the aggregate scale. So this is all fine. This is demand elasticity. This is really comfortable territory for economists. The more interesting reason that Besson points to is that the skills required to be a bank teller fundamentally changed from money handling and numeracy skills to instead requiring social skills. And this is because if you need to deposit or withdraw money, you do that at the ATM today. But if you have a complaint about your bank account, by golly, you're going to talk to a bank teller, aren't you? So they're doing the customer service and sales work for the bank now. So again, according to Besson's analysis, if you wanted to understand how ATMs shaped the future of work for bank tellers, again, you would need this granular perspective on skills and how that changed to reflect what technology could do. Okay, so here is a schematic for my answer to how we can get at this granular scale. So I'm imagining we have the US economy, which is partitioned into different labor markets, which I'm thinking of as different cities or different rural areas. It's really common to consider labor markets in isolation, but of course that's not true. There's flows of goods and people and ideas between all these different places. How would you model any one labor market? Well, a natural thing is to look at the employment distribution in that city, but I think we need to go a step further to understand the connections between different employment opportunities in that city. What are the pathways to career mobility that are available to workers, for example? What factors shape these pathways to career mobility? Tons of them, but we know that skills are one of them. It's really important if you want to get that new job that you meet the skill requirements for that job, or you're able to learn those new skills on the job as well. Skills also don't exist in isolation. There are connections between pairs of skills. Skills get bundled together. So for example, if you're good at programming and good at math, you're probably a better candidate to work at Facebook than if you're just good at math or just good at programming. And this isn't true for every pair of skills, probably programming and physical strength. Maybe there's not such a premium for that combination of skills. You can imagine that. So here, this is a cartoon, but you can see it's basically this multi-level complex system. There's connections between the top layer, middle layer, and bottom layer. There's also connections within each of these layers. And what I'm going to show you now is the work I've been doing to try to move from this cartoon to the actual empirical structure that describes each of these layers while connecting them to labor dynamics that we're familiar with. My hope is that eventually, as we fill this cartoon in, we get to a point where you can point to a specific technology, maybe a specific computer vision algorithm that alters the demand for some specific skill or ability. And by modeling within this framework, these little microscopic changes, we can accumulate these little changes into this macroscopic labor dynamics that we already talk about today. Things like job polarization, wealth inequality, access to educational institutions, and so on. We should be able to connect them all the way down to this microscopic scale. So for now, let's focus on first the layer of skills. So how are skills bundled together? Does skill polarization underlie job polarization? This bottom layer. So to study this question, I'm again going to use this skill profile data from the ONET database. This is again produced by the US Bureau of Labor Statistics. They go out and survey workers and experts across many different job titles and ask them how important a set of about 300 different skills, knowledge, and ability are to the completion of their job. We aggregate those responses to relate occupations to different skills that are variably important to them. And by looking at which skills tend to co-occur across occupations as importance, we can relate skills to one another. So which skills tend to get bundled together. In truth, when we do this, we're also going to control for ubiquitous skills using a revealed comparative advantage normalization. This is like location quotient, if you're more familiar with this. You can see that in the numerator, we're saying how important is this skill to this job as a fraction, and how does that fraction compare to the on aggregate importance of this skill compared to all skills and all jobs in the denominator. And if this whole thing is greater than 1, then that skill is more important to this job than we would expect on aggregate, and we will say that that skill is characteristic of that occupation. So that's what this bottom part here is. In truth, this math is exactly the same to the product space analysis from Ricardo Hausman and Cesar Hidalgo. Maybe some of you have seen this in the economic complexity literature. In their analysis, they weren't looking at occupations and skills. They were looking at national economies and their exports. And instead of relating skills together, they were relating products together to produce this network. In general, so what they find is that you have this network here, which has this really dense center of complex goods, things like chemicals, car parts, and computer parts, and this sparse periphery with extraction goods. So things like fishing, oil, fruit, and lumber, they're all on the periphery of the space. What they find is that developing economies tend to export the periphery goods, and more complex economies tend to export the complicated goods in these dense clusters. But as economies grow over time, they tend to make gradual movements across connected products in this network as they grow towards the complex goods in the center. So the connections between goods are important for understanding economic development. So in our analysis, we're looking at occupations and skills. And here, I would say that there was a core periphery structure that describes this network. Maybe this is what we should see since we're just borrowing their methodology here. Actually, what we see is really quite different. So here's our network of skills. Each circle is a different ONET skill, knowledge, and ability. Pairs of skills are connected together if they tend to strongly co-occur across many different occupations as importance. And here I'm coloring skills based on a more aggregated skill characterization also used by the Bureau of Labor Statistics. So if you look at the colors, you see that nodes of the same color basically end up near each other. So this is just a first order face validity check that what we find empirically is not wildly different from what the experts say the categories of skills should be. The next thing that pops out is that we don't have this core periphery structure. There's definitely, on aggregate, these two big clusters of skills. The skills on the right tend to be more sensory and physical in nature, so things like manual dexterity, strength, stamina, visual tasks, all things on the right-hand side. Things on the left-hand side tend to be more social and cognitive in nature. So programming, math, persuasion, negotiation, all skills you'll find on the left-hand side. The gap between these two skills is connected by a pretty narrow set of skills as well, right? And these are skills that are usually things like written comprehension, explanation, in general, things you might expect to learn in a college education, actually. So again, this was a completely data-driven exercise. The skills that end up getting clustered, so in principle, we could have seen no clusters, 20 clusters, 3 clusters. The data is telling us there are 2. What do these clusters tell us about aggregate labor dynamics that we know and care about already? So to explore this a little bit, we're going to project different job titles onto the skill network by coloring in with black circles the skills that are characteristic of each occupation. So these are the ones that are surprisingly important compared to all skills in all occupations. Take dishwasher, for example, on the bottom left. You see all the black circles are on the sensory physical side. This makes sense for dishwasher. What we find in general is that if you do this for occupations with higher and higher wages, moving from bottom left to top right, there's this smooth transition from relying on sensory physical skills to instead relying on social and cognitive skills. You can do something for whole urban economies. So this is combining occupation skill requirements with the employment distributions in each city to create a skill distribution, applying revealed comparative advantage in this context to identify which skills characterize which city, project those cities onto this network as well. And again, somewhat what you would expect from the occupations, cities with higher median household incomes, which also tend to be the larger cities, exhibit this stronger reliance on social and cognitive skills. So what have we done here? So I think what we have here is evidence, data-driven evidence, purely data-driven evidence to support some things we already know from theoretical work, for example, from David Otter's Hollowing of the Middle Class. So let me make this connection for you. This is the headline plot from David Otter's Hollowing of the Middle Class paper. Each line represents a different time period, a different decade. In each decade, he's ordering all job titles based on annual wage. And for each percentile bin, which he's labeling as skill, even though he's measuring wage, you can already see there's a little gap between the theory and the empirics here. He's measuring the change in employment share for each bin. And he argues that in general, you have this U shape, suggesting that employment share is growing for low skill and high skill occupations at the expense of employment for middle skill occupations. The theory that he uses to explain this trend has to do strongly with low, middle, and high skills, just like in that urbanization plot I was showing you in the early slides. But what he measured was actually wages. This was his approximation for skill. So what have we done? Well, we were completely theory-free. We just started with data. The data told us there were two major clusters of skills, and that relying on one set of skills or the other relates to wages and also relates to some of the urbanization trends we saw before. So for me, I think what we've done is provided a data-driven explanation for what low skills are and what high skills are. They're the skills in the cluster on the right and the skills in the cluster on the left. So this is great. I don't have to go disagree with David Otter, which was a real concern while I was still at MIT. But what can we do that's new and exciting here, using not just the aggregate topology, but by zooming in and focusing on all this connectivity in the skill network? So one thing we did was to use data from the census's current population survey. People contribute to the survey during a 2-year period, and if they change their job title, then we get a record of that job transition. So using that data, we're looking at how workers tend to move between these different skill sets. So what happens? Well, in general, what we find is that workers who start out in heavily physical occupations move to a little bit towards center, but generally end up stuck also in sensory physical occupations. There's sort of this similar freedom. If you're leveraging many skills on the social and cognitive side, you're able to move to other social and cognitive occupations. However, the workers who start straddling these two skill sets, they appear to be stuck. They're not able to make the full transition organically to the social and cognitive skill sets that's associated with higher wages. And actually, if you bin national employment by how strongly they rely on social cognitive skills, so this is just what fraction of your skills are in the left cluster, you see these 3 peaks, which capture these 3 different modes of behavior. So this appears to be prevalent even on aggregate. So this was where I realized we need to do a lot more to think about how skills relate to career mobility and also spatial mobility and urbanization. We're seeing a connection there as well. So to answer this question, let's now focus on this middle layer of the schematic. What are the connections between occupations that create or model or give us hints about career mobility across different cities? So to study this, again, I'm using data from ONET, but this time, instead of relating skills to one another, we're going to relate occupations to one another based on how similar their skill requirements are. When we do this, I'm going to, again, try to control for some skills that are giving us a little less information. So for example, if you look at air traffic controllers and medical surgeon, there are some skills that they have in common. So for example, getting information, retrieving relevant knowledge, and active listening. You can imagine that all these are important in both the OR and in the flight tower. But you would also agree probably that these occupations are really different. You don't want an air traffic controller doing your surgery. And also, so you can see there are some skills that are specialized to one occupation or the other. So to try to capture this, we're going to use basically Jacquard similarity here, which is comparing the intersection of skills to the size of the union of these 2 skill sets. In truth, this is a real valued version of this, but it's just, you should think about this like Jacquard similarity. So does Jacquard skill similarity predict job transition rates? We're going to answer this first using, again, that data from the current population survey, and then we're going to look at some more interesting career-long dynamics using really large data sets of workers' resume. So here we're using data from 2012 through 2018 to look at, according to the current population survey, what was the flow of workers from job A to job B at the national scale. As a baseline model, we're basically going to consider first a random mixing model, just using the national employment associated with occupation A and occupation B. And you can see that this random mixing model does a pretty good job. It gets you about 15% variance explained. We next augment this random mixing model with profiles of different occupations using the skill bias technological change framework. So not all the skill information, but just how cognitive, how physical, how routine, and how non-routine is occupation A compared to occupation B. And you get a little boost in predictive performance when you include this skill information, but you get a much larger boost when you instead use that skill similarity calculation from before, which is using a much deeper data set, a deeper taxonomy of skills. So what's going on here? Why is our skill similarity score doing so much better? Maybe it's just that we're splitting hairs here. Skill bias technological change gives me 4 variables to describe every occupation. The skill similarity, it's just one number in the regression, but we're using 300 different skills to reach that one number. So maybe there's just a couple more skills that I need to account for that would account for this improvement compared to the SBTC example. So to test for this idea, we're doing this experiment on the right. Imagine randomly selecting a subset of those 300 skills and using just those skills to calculate skill similarity. How well does Model 3 do at predicting job transition rates at the national scale? So what we see is that basically with the inclusion of the first 40 or so skills, again, randomly selecting them, there's a pretty steep improvement in general in the model's predictive performance. And then there's a more gradual, more modest, but still an improvement with additional skills thereafter. So what this does is, first of all, it rules out the possibility that it's just 1 or 2 skills doing the work. It's actually that you need many more data points in terms of skills to achieve this level of performance. I'd say that this result also suggests that there's more information about skills that we're missing out on that we could perhaps get to if we improved our data on skills, maybe more granularity and more heterogeneity as skills change from region to region. So I can tell you some more about that later on. Okay, so the skill similarity calculation seems to be useful, models a labor dynamic that we really care about. I'm happy. So I'm going to use it to construct a national occupation network. So here it is. Every circle is now a job title, and job titles are connected if they have high skill similarity. We apply some network clustering here, and then again find that in general there's 2 clusters. You're going to be unsurprised to learn that this is a separation between physical occupations and cognitive occupations. This makes sense given our analysis of skills. You can also distinguish these 2 sets of occupations based on annual wage or also their susceptibility to automation according to some of those estimates from before. Okay, so how do we use these networks to talk about career mobility? So here, well, first of all, that was a national network, but it is not the case that every city supports every occupation in the US. Cities usually support a subset of these occupations. So to capture this idea, we're going to model individual US cities by coloring in the subset of the network that represents the occupations with non-zero employment in each city. And we're also going to color in the connections between those locally supported occupations. So you can see Burlington, Vermont, Boston, Massachusetts, and Pittsburgh, Pennsylvania projected onto that national network. The gray circles are occupations with 0 employment in that city. Okay, now how might workers use, or how should we think about a worker's position in this network in terms of their options for career mobility? To try to capture this idea, remember that the skill similarity that we're using to weight these edges was predictive of job transition rates at the national scale. So to try to use this information and combine it with the network topology, we're introducing a measure that I call employment weighted embeddedness. This is basically like a weighted network degree. So pick a city, pick an occupation, sum its skill similarity to all its neighboring occupations, weighted by the employment share associated with that neighboring occupation. So it's, all right, here's an occupation. How similar are our skill sets? And are there a lot of workers in that occupation? That's what we're trying to capture here. So now you can think about this. If you have high embeddedness, that means that there are many other workers in your economy with similar skills to you. If you have low embeddedness, it means that your skills are locally rare or locally specialized, perhaps. So now the question is, does this embeddedness capture skill complementarity? Is this a good thing, something you should desire? Or is it competition? Does it represent workers who are in a competitive part of the labor market because they require similar skills to others? It could be that there's similar skills, there's economic agglomeration, and that's a good thing and you're in a good place. So to try to study this question, we're going to use 2 different large-scale resume data sets, each containing about 10 million worker resumes, one from Burning Glass Technology and another one from a company called Future Fit AI. How do workers change their positions in these networks according to this data? Well, here's an example to help you understand. This is my work history. Basically, a worker can relocate but have the same job title. A worker can have a new job title but stay in the same city, or you could change both, relocate and change your job. And you can see that I've done all three. So these are ways that workers can change their embeddedness over the course of their careers. So what do workers do? How do they change their embeddedness? Well, according to both resume data sets, workers tend to decrease their employment-weighted embeddedness over the course of their careers. So why do workers do this? Well, what we find is that individual career moves that lower embeddedness are associated with greater increases in annual wage. And this is true even controlling for some other factors. For example, controlling for if a job transition was a job title change, yes or no? Was it a relocation, yes or no? Controlling for some generic factors like what are the education, the fraction of workers with a bachelor's degree in that occupation, controlling for the page rank of an occupation in a network. So this would be using the topology, but not using employment information. But even with all these controls, we still find that embeddedness change predicts wage growth. And this is true also with year fixed effects and fixed effects for the source and destination city, where the source and destination city would be the same if you're not relocating. What about mobility between cities? So to try to study this, we're going to aggregate embeddedness scores. So basically imagine being a random worker in city 1 and looking around at your network and looking at the network in city 2 and comparing, well, what is my embeddedness in the current city? What would my embeddedness be in the next city? And using that to average over all the occupations with non-zero employment in both city A and city B to assess the on aggregate combined embeddedness of a city pair. How predictive is this of spatial mobility? We found that workers should, in general, try to decrease their embeddedness over their career. So just pointing out that if you increase your embeddedness in this calculation, this whole fraction gets smaller, right? So just pointing that out here. Okay, so we're going to test this idea looking at two different types of intercity mobility. The first is using a few years of census migration data, 2013 through 2018, from city A to city B. The second is looking at the number of enplaned passengers flying between pairs of cities using data from the Bureau of Transportation Statistics. As a baseline model, we're first going to consider the gravity model, which just uses the total employment in each city and the spatial distance between city pairs. You can see it does a good job in both cases, accounting for about a third of the spatial mobility according to both migration and flight patterns. If we include an additional parameter for this combined embeddedness score, we do a little bit better at predicting both migration and enplaned passengers, but really the best performance is achieved when you include the interaction between combined embeddedness and the combined total employment of these cities. You can see really big factors of improvement here. You can also see this visually. So this is not controlling for anything. This is just binning city pairs by their total employment on the x-axis, binning city pairs by their total migration on the y-axis, and then breaking up city pairs into quantiles based on their combined embeddedness. And you can see that city pairs with greater embeddedness have a much stronger interaction. Right, there's a stronger slope here. And also a similar result when you look at enplaned passengers instead of census migration. Okay, so we started with this cartoon and I said, let's try to fill it in with some empirical work. And I did a bunch of that. I hope you'll agree. So here we have our polarized skill network on the bottom, polarized job network in the middle. Different cities support different job titles depending on their employment distribution, but there's some spatial heterogeneity here. And I suggested that once we got to this point, we could connect the capabilities of specific technologies to specific skills and look at microscopic changes to the system and connect those to macroscopic changes. And I have not really done this yet. So this is work in progress. I'm going to leave you hanging with that. But I have some thinking that uses this whole network framework that allows me to say something about economic resilience in general. And so I'm going to tell you about this. So in thinking about how to use this complex systems approach to labor economics and what that means for the economic resilience of different labor markets, I'm actually inspired by studies of ecological resilience in ecosystems. There's a whole wealth of work that shows that you can look at the connections, the mutualistic connections between different species in an ecosystem to say how healthy and how resilient that ecosystem is to the extinction of different species or to rising temperatures or acidity levels in the ecosystem. So we're going to try to leverage some of those ideas. But first, let me help you make the connection between labor econ and this ecological body of work. How do workers find jobs? Well, there's a Nobel Prize winning economic work that describes job matching theory. In its most general form, it looks like this. You pick one labor market. There are some people who are employed who become unemployed. There are some unemployed people who find employment, and transitioning from being unemployed to employed occurs according to some matching function, which has something to do with the unemployed workers and job vacancies in your local labor market. And the question is, what should this matching function look like? Now, if you're an economist who grew up on Cobb-Douglas functions, you say, well, I'm just going to multiply these suckers together with an exponent. It's like random mixing between the population of unemployed people and the set of job vacancies in your labor market. And I'm going to give you this parameter gamma that allows you to tune how easy it is for job seekers to fill job vacancies. And that's all you get. So it seems pretty abstract, right? And actually, the people who suggested and described this theory, they know that it's abstract. In fact, they say that this formulation is a reflection at the aggregate level of the complex and varied pattern of hiring. They list a bunch of different factors that they know they're missing out on. And one of the things they hit on is this concept of skill matching. Actually, what they say is skill mismatch, which is that if you have a bunch of job vacancies and a bunch of job seekers, if the job seekers can't perform the skills that are required for those job vacancies, then you're going to have labor market friction, and unemployment will continue to grow and job vacancies will go unfulfilled. And that would be completely missed. Some of that useful information about why there's friction would be missed if you're stuck with just this model. So thinking about this, I'm going to complicate those two equations a lot, and there's going to be a big payoff at the end. So here, again, pick one city. I've done two big changes. The first is that instead of having just two equations for all the employed people and all the unemployed people, there are now is an equation for the unemployed people and employed people by occupation. The other change I've made is I've changed this matching function. Here, this Wij, that's the skill similarity between occupation I and occupation J. And then we're using that to kind of mediate how easily unemployed workers of occupation J could fill employment opportunities in occupation J. That's the idea here, right? Okay, and then a similar calculation for the unemployment equation. So when you write it out this way, okay, so hold on. What have I done here? Or I guess what do I want to say here? Okay, so when you write it out this way, if you've ever taken a dynamical systems class, or you've taken like intro to ecological simulating, you've learned about Lotka-Volterra systems. This is like, oh, you know what forward Euler is? Let's use it for this. It's like very entry-level stuff. So it's what I'm saying is that it's very well studied in the ecological literature and also in the applied math literature. And in the so what we're going to do is pull on that body of literature to help us understand economic systems instead of ecological systems. So in particular, I'm pulling from this Nature paper in 2016. In this paper, they're imagining this idealized ecosystem where you have different species of bugs that interact with different species of plants. Imagine these are pollinators. And you can project this bipartite network into two mutualistic networks, capturing, for example, which bees pollinate the same plants. And it turns out that the density of connections in this bug network tell you about how resilient that ecosystem is to the extinction of a plant, the extinction of a bug, or systemic level effects like rising temperature or rising acidity levels. So the analogy here is that instead of bugs and plants, we're talking about occupations and skills. And this bug network becomes analogous to that occupation network and those cities projected onto the occupation network that I showed you before. Okay, so how can we use the math from this paper to help us here? So one thing to note is that the changes I made to the job matching framework, I really complicated things. Instead of two equations per city, there's now 2 times the number of occupations equations per city. And there's a skill similarity score for every pair of occupations. So there's a bajillion parameters in this thing, right? So you could really easily overfit whatever you want with this thing. Turns out though, using the math from this paper, you can take this gargantuan system of equations and boil it down to just 3 things that tell you about the long-term expected resilience of a system. So first thing you need is remember that WIJ, that's that skill similarity from before. WCJ is going to be like the embeddedness calculation. So here it's ignoring local employment shares, just pick a node. What is your weighted degree in the network? That's WC. And again, this depends on what city you're in. Capital W is a normalization parameter that just controls that some cities are larger than others and will have different network sizes. Then we have these three equations: the effective employment, effective long-term unemployment, and something that I'm going to call job connectivity. So what are these three things? Well, the effective employment, you can see that it's basically looking at what is the employment for each occupation in our city, weighted by that occupation's embeddedness, and then controlling with the normalization parameter. And this average value tells us about the long-term expected employment. Similar reasoning here for the effective unemployment. The more interesting thing is to look at this job connectivity, this W effective thing at the bottom, which is basically looking at how connected, what is the density of connections within each city's occupation network. And it turns out in this paper, this is the factor that tells you the most about how ecologically resilient an ecosystem is. So that's cool, but what about economic systems? What about cities? So we were doing this work in like 2018, where the Great Recession was the labor disruption to study. Of course, now the COVID pandemic is probably more front of mind, but how does job connectivity in the year before the Great Recession relate to unemployment rates that cities experienced following the Great Recession? So here looking at peak unemployment rate. And what we find is that when you control for generic factors like city size and even other generic measurements for diversity, like what is the Shannon entropy of a city's employment distribution, what is the market depth, interactions between all these things, we still find statistically significant evidence that cities with greater job connectivity experienced lower unemployment rates following the Great Recession. So this is in line with what you would expect from the ecological studies. I know what you're thinking. What about the COVID pandemic? I'm sharing with you some preliminary results here. This is some ongoing work. I'm hoping to use that detailed unemployment data to get some new level of insights beyond just copying and pasting what we did for the Great Recession. But I can share with you some preliminary stuff here. This top time series, these are 4 different cities. This is monthly unemployment rates, total unemployment rates for these different cities. You can see that there's some variation over the last century, a few decades. The Great Recession is that hump all towards the right. And then you can see 2020 is like out of this world, huge shock to the system. Here in this analysis, I'm using data up through May 2020. Of course, we have plenty more data now, but at least using that data and looking at peak unemployment by metropolitan statistical area in 2020, we again find that once you control for city size, cities with greater job connectivity in 2019 had lower unemployment rates in 2020. So this is in line with what you would expect from the Great Recession results. So with this, I presented to you a framework for thinking about labor in the US using this multi-layered complex system. And I think that by doing this, we get some new insights into the microscopic mechanisms that shape the macroscopic labor trends we talk about already. I think that this framework gives us an opportunity to consider new data sets, things that give us more insights at skill level or education level, and more insights into heterogeneity of unemployment or heterogeneity of skill sets as well. And I think that by building this framework and continuing to work here, that there's an opportunity to improve our forecast of the future of work and improve the tools that policymakers have to create opportunities for workers who need to adapt and need to upskill and need to be prepared for these changes. If you want to learn more about this work, I've given a couple talks about this. You can find some recordings on my website. A bunch of this work is already published, so you can go read about it yourself. Some of this work is ongoing, like I mentioned, so you'll have to come to me if you want to hear more details. But I hope that you're interested and you thought this was a good presentation. So to wrap up, what's next? I want to better understand how technology changes specific demands for skills. What is this labor reorganization? Can we do a better job modeling that? What are the educational foundations or career foundations that allow workers to be adaptable to the future of work? What do I even mean by adaptable? What is the quantification of that? It's something I feel like everybody hears it and they're like, yeah, I know what that means. And I say, okay, write down an equation. And I don't know. So there's some room to figure out what we mean here. I think we need some better insights into the varied labor outcomes that can occur with technological change. For example, unemployment data that varies by occupation or varies by region, and in particular gets down to the city level. I didn't have that in this talk. I shared unemployment that varied by state, month, and occupation. Can I get down to individual labor markets, which I'm thinking about as cities? And in particular, what are the pathways and options for workers that will enable them to be productive members of the future of work? And what is the role of higher education in all this? Higher education is the source for many of the skills that we've highlighted today. It's what David Otter uses when push comes to shove to define high-skilled workers. There's something going on there. Let's try to get some data for higher ed that looks like the skills data that we have for the labor economy and be able to make a connection there between those two parts of the system. So with that, I'm happy to take any of your questions, and thank you for listening to my presentation. Josh.
So can you just speculate just a little bit based on the results you have so far on this last point about the nature of skills that we try to impart in education? Is some of these connections, for example, the paths that people follow from one job to the next, does that suggest in more detail, if we look at those particular occupations in more detail, does that suggest some kind of skills that would be very useful to the part that we maybe don't pay enough attention to now to make them able to move forward in the future?
Yeah, I think that more insight into exactly this question would be extremely useful, right? What are the sources for skills that lead to adaptability? The evidence suggests that higher ed and getting a college degree and probably getting a master's degree at least are one of those sources, but to understand exactly why, I think we need to improve. And I think a related question that's perhaps more useful to policymakers is among educational institutions, what are the variations in skills that are imparted? And how can we close that gap? So for example, if you're in a rural disadvantaged community, maybe the community college you have access to is not as up to date as CMU or Pitt. And so how does access to education limit upward mobility for those students? And how can we bridge that gap? I think this is the type of question that combines all the things you've heard about today, but it requires some new data at the skill level during higher education. And this is something we're working on right now. I have a PhD student who's slaving over a data set containing millions of university course syllabi, which include things like descriptions of learning objectives and course descriptions, which we're using to try to infer what skills students are getting from the class, and then combining that with the resume data where we know each worker's educational history and we get to see what happened to them later on. Other questions?
There's also a question on the Zoom from Eli, a PhD student here. He asked, how do you think AI threats work, which is not skill-based but has intrinsic value? For example, would the intrinsic value of art unrelated to skill level of artists decrease?
How do I think the intrinsic value of art will change with?
How do you think AI will threat the work, which is not skill-based but has intrinsic value like art?
Okay, yeah. Over lunch, I was telling Patrick that I've had this question 4 times now in the last 2 weeks. So things like stable diffusion and DALL-E, they seem like they're going to be really disruptive for the graphic design world. So what is the future of work for graphic designers? This is a great question. It certainly seems like there would be a big change in skills from requiring the manual and creative work that graphic designers do today and transitioning to prompt engineering. Seems like a very different skill set, first of all. So what about some more generic things like, will employment or wages go up or down for these workers? It's hard to say for sure, but if the demand for graphic design increases super linearly as the cost of graphic design goes down because of something like DALL-E, then I think we're in a scenario that we've actually seen before in a different context. The Industrial Revolution in manufacturing was an example where traditionally artisanal goods, who were made by only high-skilled workers, artists in their own right, you could start to produce those things using unskilled labor in these factories, right? So again, this is clearly an example of artisanal goods, art, being created by unskilled workers, people like me who can just type things into a text box and hit enter. So if I'm correct about all this, then I think what we'll find is that employment for graphic designers or artists goes up, but the nature of the job changes significantly and wages go down because many more people will be capable to be prompt engineers than are capable to be graphic designers. It's a good question, though. Yes.
Then also we see this business that like without also the abilities to get special.
Yeah. So I think the problem here is that this employment weighted embeddedness, I think it has to do with skill specialization, but you need to be more flexible with the traditional idea of skill specialization. So if you read up on some management science literature, skill specialization is usually you're very good at one particular thing, and you work in a team who are good at other particular things that together allow you to produce a good or a service. And maybe there's some management on top, right? That's the management science perspective. So what's nice about this framework is that if you organize your company this way with these different teams that all complement each other, first of all, it's efficient. You get really good at that one thing you're good at. And it becomes very easy to lop off a branch of this hierarchy if you no longer need that good or service, right? We don't need what your team does anymore. You're off the hook. You're gone. You're only good at that one thing. We don't need that thing elsewhere. That's too bad. You're gone. So there's a trade-off here between how resilient or how adaptable that worker is and how efficient the entire organization is in that framework. So this is a very microscopic view of skill specialization. The employment weighted embeddedness measure that I was talking about before is basically how many other workers are there in your local labor market that use similar skills to you. Lower employment weighted embeddedness means that your skill set is locally rare. And so I'm thinking about this as your skill set is relatively specialized compared to your local labor market. And so I think that's what's going on. You enjoy some negotiation power because that skill set you have is locally rare. It also points to the ways that thinking about skill specialization in like, oh, just get really good at Python, get really good at TensorFlow, and you can get a job in Silicon Valley, which is the type of insight you would get from traditional skill specialization. What employment weighted embeddedness tells us is that actually there's heterogeneity. It sort of differs from city to city, exactly which skills are locally specialized. So you could imagine, for example, there are lots of people who know how to use TensorFlow in Silicon Valley, probably a bunch in Pittsburgh too, but maybe in the middle of the state, in the middle of Pennsylvania, that skill would be locally rare. So if there is employment for a machine learning expert in the middle of Pennsylvania, they're going to have huge negotiating power in that labor market compared to if they were in Silicon Valley. And that's what employment weighted embeddedness helps to capture. So it's a piece of that story.
Other questions? Not, let them.
Thank you.